Hello team, this is Ruslan. In this video session, I would like to guide you through the building damage assessment documentation. We will particularly take a look to the machine learning models lifecycle, including gathering new data, creation of the data sets, training of new models, validation of your machine learning models and retrospective analysis, as well as deployment of your models to production. And as the last step, I will show you where you can find additional knowledge bases and documentation and source code while working on the building damage assessment. Everything that I'm covering today is located in our Confluence. You navigate to the Analytics Confluence page, there to R&D projects, and then to the BDA statistical model pipeline. And let's take a closer look to what are the articles we are covering today. So here we'll take a look how do you obtain the ML approach library, how do you create the datasets, and so on. All of the mentioned actions can be performed with the help of the ML approach library. Here, I would like to show you how you can install this library in your system. You navigate to this Obtain the ML approach library article, and you can see the prerequisites for this process, the actual steps that you need to run, and the expected output. Among the prerequisites, I would like to point out to the need to install the Conda and Mamba package managers into your system, as well as obtaining the latest source code of the ML approach library. Here, if you click the corresponding link, you can navigate to a more thorough instruction set. Once you have the prerequisites in your system, you can perform the installation and activation actions for the ML approach library. It consists of creating a Conda or Mamba environments, as well as installing system packages into it, including GDAL, OSGeo, and another package manager called Poetry. And with this Poetry package manager, you can actually install the rest of the required packages for the ML approach library to work. Once these steps are executed, you are able to perform the actions that we described earlier, including processing the data sets, training the ML model, validating the model, running the inference, and so on. The first stage of our pipeline is the creation of ARD imagery, necessary for creating further the datasets. The ARD imagery can be created several different ways. The easiest perhaps is to use the ARD service. A prerequisite for using this service is this ISI certificates bundle. You can navigate to the provided links in order to get more information, both about how do you create and configure a certificates bundle for your system, and how do you use the ARD service. Additionally, you can use the same ML approach library. The benefit of using ML approach library to create the ARD analysis ready data imagery is that it allows you to create your analysis ready data files in a batch mode. So for these, you use this Python function, process ARD batch sync, meaning synchronously, and you provide just the set of acquisition IDs for which you would like to generate new ARD imagery. This will interactively show you the stage of processing of your images into analysis ready data, and once
all the images are processed, you will have the complete list of images that were successfully processed into ARDs. Additionally, you can check that the corresponding run that you just created the ARD exists for this imagery. It will check the ARD meta information from the IC tool, as well as from the additional S3 buckets. And you might also download the corresponding ARD imagery that was just created. This is with the same ML approach library. Again, you might find all the further documentation here in this creation of ARD images Confluence page. Next up is the creation of so-called ground truth layers. For this, you need to refer a different documentation section, preferably this BDA masterclass. It contains a series of videos covering all of the building damage assessment ground truth details. One of which is the creation of so-called labeling applications. With the help of those S3 labeling applications, you can create new ground truth datasets. Let's take a look at one of particular examples of those labeling applications. As you can see here, you have a series of raster and vector layers, and you also have a set of tools that are to be used to label your building footprints. So you can select a set of building footprints and give them corresponding damaged or non-damaged values. For that, you would need to have ground truth, either raster or vector layer. This is covered more in detail in this BDA masterclass section. It is often the case that the ground truth is provided to you as a ready-to-use shapefile or geopackage. In that case, it is more convenient to just perform a geospatial merge between your building footprints and the ground truth that is provided to you. For that purpose, the ML approach library has this derive building footprints with ground truth function. It takes 3 input parameters, including the building footprints file path, the ground truth vector storage file path, and the geospatial tolerance, which by default is just 3 meters, which proven to be good enough. As the output, you will obtain the building footprints merged with the ground truth in just one GeoPandas data frame, which then you can save to your convenience. This eliminates the need of creation of the labeling application, and it is faster and more convenient for the ML engineers. Next up in our session is the creation of statistical datasets. Here, as always, we will see what are the prerequisites, what are the steps to initiate the creation of the datasets procedure, and also what's the expected output. So the prerequisites include the BDA ground truth, which are the geopackages containing the polygons of our buildings and the corresponding label, damaged, non-damaged, or partially damaged. As well as another prerequisite here is the analysis ready data raster files, which you can create with the ARD service, or you can refer to another article here in the same directory. How do you create the ARD files for this procedure? Next is how do you actually run the creation of the datasets procedure, but we'll maybe skip it and jump directly to the expected output. The expected output here, as the output of this procedure, are the geopackage files containing not only the polygons, the labels, but also they contain the statistical moments of the corresponding raster patch that corresponds to the polygon. The statistical moments include the mean value of the pixels, the standard deviation, skewness, and kurtosis. So these statistical moments, they will be used as features to predict or to classify if our buildings are damaged or not. As well as the nearest neighbor statistical features. So here we can see how do you actually run this procedure after providing a list of acquisition IDs and the paths to the images directory and to the ground truth directory. We also provide a path to the output directory where the datasets will be stored at. And if you didn't provide the ARD files, you can download them with this one-liner. It's a Python function that downloads the corresponding ARD files. And after everything is ready, your ground truth is ready, your ARD files are ready, you can finally run this create datasets procedure. Here we provide the images list, labels path, root directory for the images, and output directory. Outrun is the dataset creation run. It's not your ARD run name, but rather a new run name. So you can name your run as you wish. It can be absolutely arbitrary, but usually we provide the one that contains the event name. And you can provide this argument dry run, which is important. So if you say dry run is true, then you will execute every step here in this procedure except the actual creation of the dataset to see if every file can be located correctly, if the output directory can be created, and so on, before actually running the expensive dataset creation procedures. And after you see that everything went good, you can substitute this try run to false to actually run the dataset creation. This dataset creation happens in parallel, so you can provide the amount of processor of your system as the max workers here to accelerate the procedure. Next up in our session is the training of a new machine learning model. Among the prerequisites for this training procedure are the statistical datasets, which we created on the previous step, as well as training configurations. We will take a look into those configurations a little bit later. How do you run this training procedure? This is just one Python command to which you provide the Python module, which contains the training procedure, and the directory containing your training configurations. If these training procedure is successful, you will see the following output, which will contain the paths to all of the outputs of your training procedure. What is the expected outcome? First of all, the pickle file, pickle archive containing your machine learning model, as well as the configuration file used for the training of this model, inference results, and the corresponding datasets, some plots of the training procedure, including the feature importance graph and the ROC curve, and performance metrics and confusion matrix. Here I also added some code, references to the code containing the training procedures, and some other Confluence materials. Now let's take a look at some of the training configuration examples. You can find your training configurations here in the NatCat repository, in the research projects, ML approach library. So the training procedures, they are contained in the same ML approach library as all the previous stages. And here is the directory configs, and here is one subdirectory containing all the acquisition modes for Gen 3, but not only, but also the Generation 2, and one particular config. What's here in this config? You would provide the path to the output folder, the IC tool cache for those environments we don't have access to the IC tool. If you have access to the IC tool on the machine when you will be running the training procedure, you can provide an empty string here. Here I provide the common directory containing your datasets files, and the datasets files are the geo packages created on the previous stage, as I said. The format for the paths is the following. The run name of your dataset creation run. As I said, we are using the event name for that, Wildfire, meaning Wildfire event. Then acquisition mode, acquisition ID, frame number, image file name with the suffix _ML. This is actually the geopackage file name which will be created by the dataset creation procedure. As the dataset path, you can provide a local or S3 bucket name containing your datasets. Note that this file name layout is expected by the training procedure. The file names of the training datasets, they unfortunately cannot be arbitrary. I will skip most of the parameters here in the configuration, taking a look to only the most important ones. So, for example, here's the n times, is how many times do we run this optimization procedure, and usually just one is enough, because we also provide this number of hyperparameter tuning iterations, which we provide as 500, and usually that's more than enough. So overall number of hyperparameter tuning is the number times per number of iterations. So in that case, if you provide number of iterations 500, this is perfectly enough. You can provide n times equal to 1. Then the training and test parts is how many parts of your dataset, which is the combination of all of these datasets, how many parts of those do we need to use in the training or in the test dataset. If you provide 0.9 and 0.1, this will mean that 90% of all the previously provided datasets will be used as training datasets, and 10% will be used as your validation or testing dataset. You can start from just 9% and 1% of your total datasets as your training and validation parts, just to ensure that the training procedure runs and finishes successfully. Then you can increase the amount to 90 and 10% accordingly. And I'll skip some more because they are well documented. You can take a look later. I will take a look just to these filters. So these filters allow you to create a model that's particularly designed for working only with, in this case, generation tree and strip map acquisition mode imagery, but you can uncomment those additional acquisition modes and satellite generation to make your model more robust and be able to work with all of the possible generation of satellites and acquisition mode images. However, as per our observation, this leads to a performance degradation in your model. So those models are more concretely working with only one satellite generation and one acquisition mode, or a several combination of those. They are usually better than one universal model. That's it maybe about the training procedure. Next stage that I would like to take a look at is this statistical model validation or retrospective analysis. And the tools that we are taking a look at here are also suitable for downloading the imagery, running the inference, running the validation, and generating reports about our validation. So this truly depends on how do you write a configuration file for this process. What are the prerequisites? Validation library that is a part of the ML approach library. Set of models to be validated against each other, or it can be just one model. A set of ARD images if you are running the inference locally. Building footprints with ground truth if you are really running the validation. If you are running the inference only, then you don't need the ground truth. You can provide just a building footprints file. And if you are running a retrospective analysis between the human output and a given model inference results, then you may provide inference results, pre-existing inference results here as well. How do you run the retrospective? You first write a retrospective validation configuration file and run this one Python command providing a name of your validation library, which, as I said, is a part of ML approach library, and providing a path to your configuration file, validation configuration file. We'll take a look at that configuration file examples later on. If everything is successful, then you can see the finish flag and path to particular output assets. So one important output of this procedure is this validation report, which is one HTML file combining all of the other output assets. Here you can see the list of output assets that are generated as the output of this validation procedure. There's a handful of plots, performance metrics files, and so on. But as I said, they are all combined into this one validation report actually. let's take a look at one of the examples of these validation reports. So it contains radar plots for a set of metrics. Versus plots when you can compare different metrics against each other on each acquisition ID. So the top right corner here corresponds to the better model output, and down left here is when our model performed poorly in both of those metrics. So you can take a closer look then to this acquisition ID to further investigate why did the model perform so poorly on this particular image ID. And as we call it here, timeline plots. So basically here on the x-axis is the acquisition ID, and on the y-axis is particular performance metrics. So you can analyze how did the model, each particular model performed on a given acquisition ID, what kind of metric was there. You can enable only one model or compare the models against each other on a set of images. Similarly, you can compare models on all of the acquisition IDs aggregated according to your aggregation strategy. So you have several aggregation strategies: balanced aggregation, mean aggregation, max and min aggregation. So here you are comparing models against each other. So the more surface this particular model covers, the better it did on all of the metrics on balanced aggregated manner. You can compare against each other several machine learning models or even the human output. Similarly, you can analyze the performance metrics for one particular acquisition ID on the timeline plots and versus plots. Now let's jump to one particular configuration example. You can locate the validation library as part of the Notcat GitHub repository. Here you have research projects, ML approach, because this is a part of the ML approach library, configs, and here is one particular config example. In this config, we compare the outputs of the old and new machine learning models against each other. So as you can see, our config consists of these stages. Each stage is identified by its action. So if you enable this action, then it will be performed, but you can omit this action, of course, and then the whole stage will be skipped. So here, as you can see, we are downloading the given set of images. We provide the product type, ARD, and ARD run name should match this pattern. So then we will have the set of images in this output directory. This is only useful if you are running the inference locally. So here in our configuration, we are having this inference stage. Of course, this could also be omitted, and then the next stage would take control. The inference would take the images that we downloaded as the output of the previous stage. We'll take these polygons file and we'll create the inference results here in this directory, ML inference new, meaning that it will take the new machine learning models. You provide also the model IDs here. This means that those models should be deployed. At the moment, this pipeline cannot run the inference of the computer vision model. However, this can be easily integrated into this pipeline as well. Once you have the inference results, you can run the validation. For that, you would also need to provide the building footprints with the ground truth, because for validating the model output, you need to have the ground truth. Provide the building footprints with the ground truth, action validation. You provide of course, the inference results. This can either be the output of the previous stage or an existing inference results directory. And here you provide the inference results pattern. What kind of files should you find? Should you try to locate in this inference directory? As you can see, we are locating geo packages, but these can be anything that GeoPandas can open, for example, shape files. You just provide a pattern and it will try to locate the inference results itself. The only important feature it must contain are the polygons and damage column. Once the validation process is complete, it will create the validation metrics as this output. Here's the output of the validation process. Here we are running a validation of another model. So for these, for this ML inference new, we are taking the inference results from our previous stage. For this other machine learning model, we are expecting pre-existing inference results. So as you can see, this pipeline is pretty flexible. You can either run the inference locally for each of the validated models, meaning that you will be obtaining the inference results locally. Either you could provide the pre-existing inference results, for example, from our BDA service, meaning the inference results delivered to our clients. You could also compare your model's performance against something that you deliver to your clients. And the last stage is this report stage, for which you would provide your validation results metrics. Here, the key is how these inference results, they will be visible in the report file. Additionally, you can provide this metric preprocessing dictionary. This will substitute all the names that are matching this pattern with this pattern. So here we are changing the name dataset acquisition ID assessment.geopackage to release and acquisition ID. So here's the capture group. Capture group captures acquisition ID and it's substituted here. So then in the report, in the timeline plots, that's the way you will see them. You will see only on the x-axis, you will see only the acquisition IDs. Otherwise, you would see the entire geopackage name. And here are the metrics to be included in each of the types of the plots, including the radar plots, what kind of metrics to include. So as you can see, here are 6 types of metrics. That's why these radar plots are hexagonal. But you can remove some metrics if you are not interested, and then the radar plots would have less or more angles and less or more features. The timeline plots basically will contain these particular performance metrics against each particular acquisition ID. And this directory versus plots is what metrics would you compare against each other for each particular acquisition ID. You would also provide the output directories and the style of your reports. I would also mention that the particular retrospective outputs shall be located in the retrospective directory in our ML approach GitHub repository in order to appear in our GitHub pages. So as you can see here in this retrospective directory, we have this report HTML, which landed to our GitHub IO GitHub pages. This is because we have automated these GitHub pages generation CI/CD pipeline, and now we can refer to this retrospective whenever we want. If you create new retrospective, please add these retrospective to retrospective directory. This way it's always in our repository and we can observe it in the future. The last stop in today's session is the deployment of your model to production. Once you're ready to deploy your newly created model to production, you follow the next steps. You first upload the newly trained model and all of its artifacts to the given S3 bucket. Most importantly, you upload there the pickle archive of the model, the binary scalar that's created by the scikit-learn library, and all of the training and testing datasets, so the entire dataset. This is obvious why the model itself should be there in this bucket. The training and testing datasets should be there because we are retrieving the features names and their order from the datasets. This is because we are training on NumPy arrays and not the pandas data frames. So that's why the names of the features are not saved alongside our models. So we need to retrieve the features names and their orders from the dataset itself. Last, this is the robust scalar that is needed to scale the feature values properly so the inference results are correct. Let's go to this bucket and I'll show you a couple of examples. So here, as you can see, there's these test datasets, robust scalars, and the model pickle archives. So the central part is the model ID that will be used to identify the model. And recently we started using this date and time of creation of your model as its model identifier. The prefix is model underscore and the suffix or file extension is the pickle, PKL. Once you've uploaded the model to deployment bucket, you can also correspondingly change the source code of the building damage assessment service. So this model is used as the default one. If the user did not provide the model identifier, your model can be used as the default one. For this purpose, you change the value of the following variables. This is in the NatCat repository, projects, building damage assessment source code, and the file is models.py. Then you change the ML model identifier, meaning this is the model responsible for the strip map acquisition. You change it to the corresponding model ID. And this is the model identifier responsible for every other acquisition mode. You change it either to the same model ID or to a model ID that is more suitable for high resolution acquisition modes and for the sled. Once you've performed those two deployment actions, you can inform the data engineering team. For that, you reach to this Slack channel and let the data engineering team know that your models are ready to be deployed in staging. Once you check that the model is functioning properly in staging environment, you can further let the data engineering team know that you are ready for the deployment in production. That concludes our today's session. You also can check these databases and data storages document. These collects all the Jira boards, GitHub repos, knowledge bases, and S3 buckets that may be important for your work on this ML approach library and on the building damage assessment products. Thank you for your attention and have a great time working with this documentation.